first lecture we just learnt about some basic definitions related to essential thermodynamics that will make us understand phase equilibria. So in this lecture we will again continue building on that, and we will see some more thermodynamic correlations. So we were studying about how phase equilibria is important in understanding phase transformation. For example, I gave you the example of water in which H2O molecules go from H2O molecules are present in liquid phase at temperatures lower than 100 degrees centigrade, but as you go beyond 100 degrees centigrade they transform into gaseous phase. And the reason for that lies in the thermodynamic equilibrium, because at higher temperature the vapor phase is in the equilibrium state, whereas at lower temperature the liquid phase is in the equilibrium state, and this is determined by what we call as free energy. The free energy of liquid phase is lower at lower temperatures as compared to vapor phase, whereas converse is true at high temperatures. So now let us look at the aspects related to phase stability. So we look at what we call as phase stability. Phase stability basically is determined by thermodynamics, and in particular so basically what we are looking at a given condition of given temperature, pressure and composition, what are the stable phases, and this is what is phase equilibria. So let us first define the term called as free energy. So I assume that you have basic knowledge of elementary thermodynamics, which is useful to understand the course. So free energy, so at a constant, at a given temperature and pressure as well as composition, free energy G, this is G determines the phase stability for an alloy, okay, and G is called as Gibbs free energy, and this G is written as H minus Ts. So H is called as enthalpy, T is the temperature, and S is called as entropy. So let's just look at the definitions of these components. So let's first look at what is enthalpy. So enthalpy is essentially defined as H, okay. It is essentially defined as heat content of a given system, and H is defined as further U plus PV, where U is the internal energy, P is the pressure, and V is volume, okay. And this U essentially, so basically it is that enthalpy, you can say the total energy inbuilt in a system, which consists of the internal energy and which consists of the pressure and volume terms, the net amount of work which is done by the system or on the system, and that will determine the total heat content of the system. So let us now first look at the internal energy. So this U is basically sum of all the kinetic energy contributions and all the potential energy contributions. So, kinetic energy may arise from, let us say, A, atomic vibrations, B, it could be due to, so atomic vibrations in both solid and liquid phase, it could be because of translational and rotational energies of atoms or molecules. So, so it again could be within the liquid phase or gas phase. Generally, these are more of significant in liquid and gas phase, whereas atomic vibrations are more in gaseous phase. So, this is the kinetic energy term. So, the potential energy term on the other hand is written as follows. So, this is potential energy term is potential energy Pe, which is due to bonding. It is also because of atomic or molecular interactions, because it may not be only bonding, it could be various other things such as hybridization and things like that, interactions in a system. So, this is what the total energy now will be. So, you have kinetic energy and then you have potential energy. Now, let us look at the total energy is equal to kinetic energy plus potential energy. The kinetic energy is because of atomic vibrations and which could be in solid and liquid both forms, as well as translational and rotational energies of atoms and molecules, whereas potential energy is because of, as I wrote just now, is because of bonding and inter-atomic interactions. So, this gives rise to total energy. So, total energy now would be Ke plus Pe. So, basically as you change the temperature, the internal energy increases. Now, why does it happen like that? So, when you go from, for example, water to vapor, for instance, water to vapor, essentially you go from low temperature to high temperature, and basically you are adding heat to the system. So, your internal energy will go up as you go from water to vapor. Similarly, let us say if you heat a solid, you increase its energy because you add heat. Similarly, if you heat, for example, let us say tungsten filament bulb, the tungsten filament becomes red hot, and which means its internal energy increases, and as it cools down, its internal energy decreases. So, now if I just give you the signs of these energies. So, if you have, let us say, a system, and then you have surroundings, and so basically if you do, so this is, let us say, on this side you write work, on this side you write heat. So, if work is done onto the system, then delta E is delta U, let us say delta U is positive, and if you do work, if system does the work, then delta E is negative. On the other hand, in terms of heat, if system releases the heat, then delta E is negative, and if system absorbs the heat, then delta E is positive. So, that is how you distinguish between various states of the system as you decrease or increase the temperature. Now, second thing that we talk about is the PV term. Okay. The PV term is of importance because phase changes are affected by the change in the volume or the pressure. So, when we say H, so this P, when we say H is equal to U plus PV, so it is this term which adds or which adds or which becomes plus or minus as depending upon the what the magnitude of this term is. So, basically for mostly condensed phases, in general for condensed phases by this I mean generally liquids and solids, the delta PV term is generally very small and hence it is generally neglected. So, for condensed phases generally H is nearly equal to you can say U, if this delta PV term is very small. And finally, we come to the third term in G minus Ts, that is what is called as entropy. And this entropy is nothing but a measure of randomness, measure of randomness or measure of disorder of species within a given system, and this again has a strong bearing on the overall stability of the system. So, as now we come to the first expression again, G is equal to H minus Ts. The free energy of a given phase is affected by the overall heat content H, which is equal to U plus PV. In most cases it is equal to U for solid phases and then Ts term. So, whether enthalpy increases or decreases or the entropy term increases or decreases under given set of thermodynamic conditions will determine whether G will increase or decrease as a function of temperature or pressure for a given system. Now, let us look at the definition of what we call as equilibrium. So, what is equilibrium? Right. Equilibrium is defined by generally we defined as equilibrium as in the context of materials, the most stable state, that is no change happens if you leave the system on its own under a given set of parameters. So, basically you can define equilibrium as most stable state of a system under given set of temperature, pressure and composition. So, basically if T and P are, you can define if these are constant, then dG is equal to 0, and what it means is that free energy has a minimum under those conditions. Okay. So, generally if you look at again G is equal to H minus Ts. Okay. So, G will decrease when H is small. So, if you decrease H, your G will decrease, and when you increase entropy, the G will decrease because there is a negative term. So, generally speaking, the free energy decreases when enthalpy decreases or entropy increases, because minus Ts term goes as negative and H term, of course, it has to decrease for the but overall it is a combination of these two which will govern whether free energy will increase or decrease for a given system. And generally what we are interested in knowing what is the relative change in free energy for given phases. So, it might happen that you have two phases, and as the function of temperature the free energy of both phases decreases, but if the decrease in the free energy for one phase is happening at a higher rate as compared to the other phase, then we may come across a temperature at which the free energy of the phase for which the free energy decrease rate was higher may lead to lower free energy as compared to the other phase. So, we will see those changes later on. So, generally, so let us say at lower temperatures, generally what happens is that at lower temperatures, basically at lower temperatures you have higher atomic interactions, okay, and higher atomic interactions will lead to higher binding, stronger binding, and this generally leads to low or more negative, you can say, internal energy, because and that is why solids have lower internal energy or more negative internal energy as compared to the liquids. Gases have, if you compare solid, liquid and gases, solid will have the most negative internal energy, whereas liquids and gases will have more positive internal energy as compared to the solid. So, as a result, generally because of this decrease in the internal energy or negative internal energy of the solids, solid phases are more stable at lower temperatures. So, we can say if you go to why this is what makes solids stable, whereas at higher temperature converse happens. At higher temperatures your solids have, your liquid and gases have, although they have, so if you look at higher temperatures, higher temperature we see generally liquids are stable, right. This happens is equal to H minus Ts, although their H is positive, although there is more, although the H is more positive as compared to the solid, the entropy is higher. So, again this entropy term dominates, this term dominates over the H term. So, H increases, but S also increases. So, the competition between these two makes lower than Gs, whereas at temperatures Gs is lower than Gl in general. So, we will look at various systems, a few systems later on. So, at higher temperature term dominates, lower temperature the enthalpy term dominates, giving rise to stability of solids and liquids at lower and higher temperatures. Similarly, you have pressure volume effect as well. As we said, generally pressure volume effects are not generally considered, but however, if they are present they have to be considered, and hence the systems with smaller volumes are preferred as compared to system with higher volumes because of lowering of PV term. So, if you look at this H is U plus PV. So, this volume term comes into picture at a given pressure. If you have two phases, the phase with a smaller volume will be preferred as compared to phase with higher volume, and this is because of changes in the corresponding changes in enthalpy. So, if your enthalpy has to at higher, so if you have two phases, another one phase with lower volume that will have lower enthalpy as compared to the phase with the higher volume. So, more negative enthalpy has to be, will be preferred, or lower enthalpy will be preferred as compared to the other phase. So, when we define equilibrium in totality, the equilibrium in totality is defined as you plot G as a function of, let us say, arrangement of atoms. So, if I make a plot of this, so this is for example the situation, you have a state A and you have a state B. So, you can see that there are two minima here. So, dg for this is also 0, dg for this is also 0. However, in totality, if you look at that free energy landscape, this B state has lower energy as compared to, so this is, let us say, GB, and this is, let us say, GA. So, GB is more stable at equilibrium because GB is lower than GA. So, if you leave the system for long time to achieve equilibrium, system will move towards achieving GB. However, in many systems such as in glasses, there are, or in polymers, there are metastable states which have local minima. So, this local minima is often stable because this is also at an energy which is small at a at this arrangement. However, to reach from here to here, it has to overcome energy barrier. So, this is energy barrier, okay, delta, let us say Q. This energy has to be overcome for system to again achieve a low energy state. So, as a result, typically some sort of impetus has to be provided for system to move from this state to that state. So, this happens generally in glasses. In glasses, there are local minima in energy, and the system stays in that energy because the delta Q can be quite large for system to achieve the proper equilibrium. However, for many crystalline systems, for many solids, the minima is achieved quite fast. So, minima, how fast or how slow minima is achieved, that is determined by the kinetics or the time dependent rate processes within the system, but generally the tendency of a system, if you leave it enough for long enough time, it will achieve the equilibrium with lowest free energy state. So, for example, if I give you, I will give you the example of diamond, carbon. So, carbon, if you leave it for long time, the thermodynamic state, stable state of carbon is, it has two forms, one is graphite, second is diamond. Diamond is the metastable form and graphite is a stable form. But we do see diamond exists, okay. We do see that diamond exists, and however, if you leave diamond long time, for very long time, diamond will eventually convert to graphite. So, if you, but the process is so slow that for virtually for very long times, for virtually for eternity, the diamond appears as if it is stable, but within size of earth, the timeline of earth is very long. As a result, the phase transformations that happen from diamond and graphite, they do not happen in our lifetime, they take millennia for them to happen. Similarly, glasses, the crystalline glass is more stable as compared to amorphous glass, but what we see in front of us is mostly amorphous glass because the time scales at which amorphous glass which convert into crystalline glass are huge. They are way beyond our imagination. So, that is why you see these metastable states appear to us as if they are the stable phases. However, since these are local minimas and free energy which are not absolute minimum, as a result they are that is why they are called as metastable states which do exist for long times in front of us. So, we will stop here today. What we have learnt is basically in this lecture, if you go from the beginning, we learned the concept of free energy, what free energy is, what are the terms which are included in free energy. So, free energy is required to understand the phase stability, and free energy consists of three terms: enthalpy, temperature and entropy. Enthalpy is basically the heat content of the system. So, heat content depends upon the internal energy in the PV term. By and large, it is governed by internal energy itself. So, internal energy is sum of potential energy and kinetic energy, and these are kinetic energy comes from atomic vibrations and translation rotation energy of atoms molecules, whereas potential energy is primarily because of binding or bonding between the molecules. So, So, it is a competition between enthalpy and entropy which gives rise to eventual lowering of free energy in the system, determining the final phase stability. Entropy, as I said, is the measure of randomness of a given system. So, in the next few lectures we will again expand on these and establish a basis of phase equilibrium. Thank you.